Earth's surface by eroding soil and bedrock. The flowing water carries the eroded sediment downslope. A stream may deposit some of the sediment in the valley down which it flows, while it carries the remainder to a lake or to the sea, where the sediment accumulates. Stream erosion and sediment transport depend on a stream's energy. A rapidly flowing stream has more energy to erode and transport sediment than a slow stream of the same size. The competence of a stream is a measure of the largest particle it can carry. A fast-flowing stream can transport cobbles and even boulders in addition to small particles. A slow stream carries only silt and clay. The capacity of a stream is the total amount of sediment it can carry and is proportional to both current speed and discharge. Thus, a large, fast stream has a greater capacity than a small, slow one. Because the ability of a stream to carry sediment is proportional to both velocity and discharge, most sediment transport occurs during the few days each year when the stream is in flood. Relatively little sediment transport occurs during the remainder of the year. So flooding streams are usually muddy and dark, but the same stream may be clear during low water. After a stream erodes soil or bedrock, it transports the products of weathering downstream in three ways. One way is in the form of ions dissolved in water, called the dissolved load. A stream's ability to carry dissolved ions depends mostly on its discharge, its pH, and the geology over which the stream flows. A stream flowing over volcanic bedrock will have a higher dissolved load than the same stream flowing over quartzite bedrock, because the volcanic rock is more chemically reactive than the quartzite. Although dissolved ions are invisible, they comprise more than half of the total load carried by some rivers. More commonly, however, dissolved ions make up less than 20% of the total load. If you place soil with equal amounts of sand, silt, and clay in a jar of water and shake it up, the sand grains settle quickly. But the smaller silt and clay particles remain suspended in the water as suspended load, giving it a cloudy appearance. Clay and silt are small enough that even the slight turbulence of a slow stream keeps them in suspension. A rapidly flowing stream can carry sand in suspension. During a flood, when stream energy is highest, the rushing water can roll boulders and cobbles along the bottom as bed load. Sand also can move as part of the bed load by rolling or bouncing along the bottom while being carried downstream by the current between bounces. Downcutting and base level a stream can erode both downward into its bed and laterally against its banks. Downward erosion is called downcutting. The base level of a stream is the deepest level to which it can erode. Most streams cannot erode below sea level, which is regarded as the ultimate base level. In addition to ultimate base level, a stream may have a number of local, or temporary, base levels. For example, a stream stops flowing where it enters a lake. It then stops eroding its channel because it has reached a temporary base level. A layer of rock that resists erosion may also establish a temporary local base level because it flattens the stream gradient, causing the stream to slow down and erosion to decrease. The top of a waterfall can be a temporary base level established by resistant rock. For example, Niagara Falls is formed by a resistant layer of dolomite overlying softer mudstone. The dolomite forms a temporary base level for the stream by resisting erosion, but the turbulent falling water undermines the soft mudstone at the base of the falls, causing the overhanging dolomite cap to collapse and the falls to migrate upstream. In this way, Niagara Falls has retreated 11 kilometers upstream since its formation about 9,000 years ago and is slowly eliminating the temporary base level formed by the dolomite. Carol Gallas Shutterstock.com EB Adventure Photography Shutterstock.com Ritu Manoj Jethani Shutterstock.com. A stream like that in Figure 11.8a erodes rapidly in the steep places where its energy is high and deposits sediment in the low gradient stretches where it flows more slowly. Over time, erosion and deposition smooth out the irregularities in the gradient. The resulting graded stream has a smooth, concave upward profile. Once a stream becomes graded, there is no net erosion or deposition and the stream profile no longer changes. An idealized graded stream such as this one does not actually exist in nature, but many streams come close. Sinuosity of a stream channel. Steep mountain stream usually downcuts rapidly compared with the rate of lateral erosion. As a result, it cuts a relatively straight channel with a steep-sided, V-shaped valley. The stream maintains its relatively straight path because it flows with enough energy to erode and transport any material that slumps into its channel. In contrast, a low-gradient stream is less able to erode downward into its bed. Rather, much of the stream energy is directed against the banks, causing lateral erosion. Lateral erosion occurs where a low-gradient stream forms a series of bends, called meanders. As a stream flows into a meander bend, the water pushes against the outside bank of the meander, much like your body leans against the inside of our car while going around a sharp curve at highway speed. As water is pushed against the outside bank, it causes the bank to erode. The water also causes the deepest part of the channel to form adjacent to the outside bank, creating an asymmetric bottom profile from bank to bank. The water piling up against the outside bank causes the flow around the inner bank to be both shallower and slower and promotes the deposition of sediment there, forming a point bar. Through time, the point bar builds further and further out into the river as the outside bank of the meander is eroded back. In this manner, the meander slowly migrates laterally toward its outside bank. Occasionally, such lateral migration of a stream causes it to cut across the neck of a meander, forming a shortcut and isolating an old meander loop. Although it no longer has an active flow, the abandoned meander loop remains full of water and becomes an oxbow lake. Meandering streams typically form in regions of very low slope gradients. In addition, meandering streams typically carry a large suspended load that includes an abundance of clay. During floods, the mud is carried onto the adjacent floodplains where it settles out and is deposited. Subsequently, this clay-rich mud is exposed along the banks of the river, especially along the outside of meander bends. As anyone who has spent time making ceramics knows well, wet clay is sticky. This sticky nature allows riverbanks made of clay to become very steep or even overhanging without collapsing. The abundance of vegetation further helps stabilize the banks of meandering rivers. As a result, meandering streams typically flow in a single channel that changes slowly through the process of lateral migration described previously. In contrast to meandering streams are braided streams that flow in many shallow, interconnecting channels. A braided stream forms where the supply of sediment exceeds the stream's capacity, that is, more sediment is available than the stream can carry. The excess sediment accumulates in the channel, forming a series of sediment bars. During low water, the stream flows simultaneously in multiple channels that pass around the bars. During floods, the bars may be completely submerged, and the higher discharge may cause the bars to migrate downstream a short distance, while changing shape in the process. As a result, braided streams often look different from year to year. Unlike mud-dominated meandering streams, braided streams are dominated by their coarser-grained bed load. As a result, braided streams usually are found in regions with higher slope gradients where coarse-grained sediment is generated through erosion. Braided streams also are common in both desert and glacial environments because both produce abundant coarse-grained sediment. A desert yields large amounts of sandy sediment because it has little or no vegetation. To prevent erosion, glaciers grind bedrock into sediment, which is carried by streams flowing from the melting ice. Unlike clay-rich banks of meandering streams, the banks of braided streams usually are made of coarser-grained sand and gravel particles that don't stick together, unlike clay-sized particles, but rather collapse at slopes steeper than the sediment's angle of repose. As a result, the relatively coarse-grained sediment forming the banks of braided rivers quickly is eroded from the bank into the channel, contributing to the high bed load characteristic of braided streams. Figure 11.13. Drainage basins and drainage divides only. Dozen or so major rivers flow into the sea along the coastlines of the United States. Each is fed by a number of tributaries, which are in turn fed by smaller tributaries. The region drained by a single river is called a drainage basin. At the edge of each drainage basin is a drainage divide, an imaginary line on the ground separating adjacent drainage basins. The most famous drainage divide in North America is the Continental Divide. Water runoff east of the Continental Divide drains into stream tributaries that ultimately lead to rivers flowing into the Atlantic Ocean, whereas runoff west of the Continental Divide eventually reaches the Pacific Ocean. Other important North American drainage divides separate the Columbia and Colorado River drainage basins west of the Continental Divide and the Rio Grande from the Mississippi River drainage basins east of the Continental Divide. Collectively, these four drainage basins cover 3/4 of the lower 48 United States. Stream erosion and mountains. How landscapes evolve according to a model popular in the first half of the 20th century. Streams erode Earth's surface and create landforms in an orderly sequence. At first, they cut steep, V-shaped valleys into mountains. Over time, the streams erode the mountains away and widen the valleys into broad floodplains. Eventually, the entire landscape becomes a large, featureless plain. However, if this were the only mechanism affecting Earth's surface during its 4.6 billion-year history, all landforms would have eroded to a flat plain. Why do mountains, valleys, and high plateaus still exist? The model tells only half the story. Streams do continuously erode the landscape, wearing down mountains and widening floodplains. But at the same time, tectonic activity may uplift the land and interrupt this simple, idealized sequence. In this way, Earth's hydrosphere and atmosphere work together with tectonic processes in the geosphere to create landforms. Geomorphology, from the Greek words for earth forms, is a branch of geology that deals with the evolution of landforms through time. Stream deposition. When streams slow down, they deposit their bed load first. If water slows sufficiently, the suspended load may also settle to the bottom. Sediment deposited by moving water is called alluvium. When alluvium is deposited, new landforms are created. For example, if a steep mountain stream flows onto a flat plain, its gradient and velocity decrease abruptly. As a result, the stream deposits most of its sediment in an accumulation called an alluvial fan, named because the shape of the deposit resembles a handheld fan. Alluvial fans are common in many arid and semi-arid mountainous regions, where they commonly occur where a fault has caused a mountain range to be uplifted relative to the adjacent valley. In areas characterized by active faulting, it is common for the upper portion of an alluvial fan to be cut off, or beheaded, from the lower portion of the fan as the fault continues to move through time. As the fault accumulates more offset through time, the lower portion of the fan slowly is buried as the valley fills with sediment, whereas the upper portion, the head, of the fan is uplifted as part of the mountain front where it is usually eroded. A stream also slows abruptly where it enters the still water of a lake or an ocean. The sediment settles out to form a delta, a nearly flat-topped landform with a steep frontal face. The upper surface of the delta, called the delta top, extends beyond the shoreline to the more steeply sloping, sandy delta front. Further offshore is the more muddy prodelta. Both deltas and alluvial fans are commonly fan-shaped and resemble the Greek letter delta. The fan shape is produced by distributary channels. Unlike tributary channels that merge in a downstream direction, distributary channels split in a downstream direction. Distributary channels on a delta carry sediment beyond the shoreline, where it accumulates in mouth bars that form where the distributary channels end. As a mouth bar grows in size, flow from the distributary must diverge to get around it. At the same time, sediment is deposited on the bed of the distributary channel, causing it to become less efficient at transporting water and sediment. Ultimately, these inefficiencies become so great that the distributary channel is abandoned and the water and sediment flows down a new channel established on a different part of the delta. This process of channel abandonment and re-establishment elsewhere is called avulsion and usually takes place when the river is in flood. As sediment is added to alluvial fans and deltas, they build outward. Most alluvial fans are relatively small, covering areas ranging from less than a square kilometer to a few square kilometers. In contrast, a large delta may cover thousands of square kilometers. Although sediment is deposited on the delta top by flooding rivers, much sediment also is deposited beyond the mouths of the distributary channels, on the delta front and prodelta. Even though deltas cover only a small fraction of Earth's total land surface, they are environments that involve each of Earth's 4 spheres. The delta is composed of solid sediment, but it is a watery zone where branch distributaries meet open water and much groundwater is contained between the individual sediment grains in the delta. Because floods regularly deliver nutrient-rich sediment to deltas, they typically are fertile, and delta ecosystems are rich in natural plant and animal life. The fertile soils and easy access to transportation systems make deltas desirable places for human habitation, but the elevation of delta land along the coast is barely above sea level and the river elevation, so it is certain to be flooded during atmospheric disturbances such as heavy rains and hurricanes. Floods. When rainfall is heavy or snowmelt is rapid, more water flows down a stream than the channel can hold, creating a flood. During a flood, the stream overflows onto low-lying adjacent land called the floodplain. Massive floods occur somewhere in the world every year. The following 3 recent cases are good examples. During the late spring and summer of 2008, heavy rain soaked the upper Midwest. Parts of eastern Iowa experienced 15 to 20 inches of rain in 1 month. As a result of the intense rainfall and abnormally heavy snowpack, the Mississippi River and 9 Iowa rivers crested at or above record levels. In St. Louis, the Mississippi River crested 7 feet above normal. The Cedar River crested at over 32 feet, flooding 9.2 square miles of Cedar Rapids, Iowa, exceeding the highest recorded flood levels from 1929 and causing an estimated $1.5 billion damage in the city alone. The floods killed at least 24 people and injured hundreds more. Damages to the Midwestern states exceed $6 billion. In April of 2011, 2 major storm systems combined with the melting of the winter snowpack to swell the lower Mississippi River to record levels. The flood was big enough that the Army Corps of Engineers, responsible for managing runoff from the river, decided that it was necessary to open several floodways, areas of historic floodplain that can be reconnected to the river during floods to lower the water level in the river and protect communities downstream. Although designated in the 1930s to serve as relief valves for future floods, the floodways are not empty lands, but rather contain numerous farms. On May 3, the Corps blasted a 3-kilometer hole in one of the Mississippi River levees in an effort to save the town of Cairo, Illinois. The breached levee caused the river level near Cairo to begin falling before the crest of the flood arrived, ultimately saving the town but flooding over 500 square kilometers of rural farmland in Missouri. 11 days later, the Corps began opening floodgates on the Morganza Spillway in Louisiana to prevent major flooding in Baton Rouge and New Orleans downstream. The opening of the floodgates diverted water into the upper reaches of the Atchafalaya River. Because floodgates had not been used since 1937, there was some risk that too much water would be diverted from the lower Mississippi River, causing it to abandon its current channel and reroute down the Atchafalaya River. Fortunately, the river did not do this, but the 2011 Mississippi River floods caused an estimated $2 billion in damage and resulted in the evacuation of thousands of homes. Despite these significant damages, the management of the 2011 floods likely prevented a much worse scenario. A much larger flood-related disaster in terms of human lives occurred in June of 2013 in northern India. Over a several-day period, unusually heavy warm rain from the annual monsoon as well as several heavy cloudbursts fell in parts of the southern Himalayan mountains. The rains melted large volumes of glacial ice in the mountains, sending huge quantities of water downstream toward the adjacent lowlands. In addition, the rain saturated the ground and caused numerous landslides. The disaster that resulted was compounded by the proliferation of roads, hotels, shops, and multi-story housing in landslide and flood-prone regions and the construction of dams that blocked drainages and changed the distribution of water draining out of the mountain tributary system. The recently constructed dams and newly formed landslides blocked the flow of water downstream, causing villages to be inundated with water and mud. By June 28, 2013, over 1,000 humans were reported dead and 70,000 were either stranded or missing. Flood control. Because deltas provide natural access to transportation waterways, contain level and fertile soil for agriculture and generally contain abundant wild game, deltas have long been desirable places for humans to live. However, flooding is a natural part of delta evolution, and all deltas undergo flood when sufficient discharge is supplied from the river that feeds it. As a result, humans have developed several strategies for controlling floods so that, despite their inevitable occurrence, the damage floods cause can be minimized. Flood control, while providing relief from flood waters for some, may exacerbate flood-related damage for others. Artificial levees and channels. An artificial levee is a wall built along the banks of a stream to prevent rising water from spilling out of the stream channel onto the floodplain. In the past 70 years, the U.S. Army Corps of Engineers has spent billions of dollars building 11,000 kilometers of levees along the banks of the Mississippi and its tributaries. Of course, levees can fail, resulting in significant flooding. In 2008, at least 20 levees along the Mississippi River failed, resulting in widespread flooding and damage across parts of Iowa and Indiana. Unfortunately, artificial levees create conditions that may increase both flood intensity and property damage. One factor is entirely human. The protection promised by levees encourages people to build in the floodplain. In the absence of a levee, people might decide to build on high ground that is safe from floods. But when levees are built, people are more likely to construct homes and businesses in harm's way. Levees also can cause higher floods along nearby reaches of a river. By restricting the channel, artificial levees form a partial dam that raises the water level and increases the risk of flooding upstream. In addition, because the stream cannot overflow levees during small floods, sediment that normally would be deposited on the floodplain is deposited within the channel, raising the level of the stream bed. After several small floods, the entire stream may rise above its floodplain, contained only by the levees. This configuration creates the potential for a truly disastrous flood, because if the levee is breached during a large flood, the entire stream flows out of its channel and onto the floodplain. As a result of artificial levees and channel sedimentation, portions of the Yellow River in China now lie 10 meters above the adjacent floodplain. Thus, levees may solve flooding problems in the short term, but over a longer time frame they can cause even larger and more destructive floods. Flood control, the Mississippi River Delta, and Hurricane Katrina in August 2005. Hurricane Katrina drove storm waters over the levees protecting New Orleans, flooding the city, chasing 1.3 million people from their homes, and causing approximately $200 billion in damages. This problem was exacerbated by decades of flood control practices along the Mississippi. In a natural system, a delta builds upward and extends seaward by sediment deposition, although the front of the delta is eroded by ocean waves and currents. In the past 50 years, deposition rates in many coastal deltas have decreased significantly, in part because dams built upstream have trapped sediment that otherwise would have reached the delta. The construction of levees along distributary channels on the delta also has caused sediment to bypass the delta rather than be deposited on it during floods. Contributing to coastal erosion is the urban and agricultural destruction of natural plant communities that normally hold the soil together and global sea level rise that causes the wave energy to reach further inland. Other problems affecting the delta include the rising global sea level and the sinking, or subsidence, of the land surface, as the delta sediments compact and expel water from their pore spaces. As a result of all these processes, the Mississippi Delta has shrunk. Between 1930 and 2012, nearly 5,000 square kilometers of the delta sank below sea level. One recent study estimated that by the year 2100, an additional 10,000 to 13,500 square kilometers will be submerged, an area roughly the size of Connecticut. The flooding of New Orleans in 2005 is an example of both a complex systems interaction and a threshold event. While Hurricane Katrina triggered the flood, human interference and development within a complex natural river delta system set the stage. Over the previous decades, the global sea level rose while the delta subsided and slowly eroded. Natural buffers were removed, with no immediate ill effects. Then a catastrophic storm pushed waters inland. The levees failed, causing a huge human disaster. Although it is easy to point to the hurricane as the cause of the 2005 disaster, the other factors that combined to make this such a devastating event were known well in advance. In 1995, the senior authors of this textbook wrote, "If current rates of erosion continue, the sea will flood New Orleans, causing severe economic losses." Tragically, this dire prediction was accurate. Floodplain management, as we have shown, in many cases attempts at controlling floods either do not work or they shift the problem to a different time or place. An alternative approach to flood control is to abandon some flood control projects and let the river spill out onto its floodplain. Of course, the question is what land should be allowed to flood. Every farmer and homeowner living on the floodplain wants to maintain the levees that protect it. Currently, federal and state governments are establishing wildlife reserves in some floodplains. Because no development is allowed in these reserves, they will be permitted to flood during the next high water. However, a complete river management plan involves complex political and economic considerations. Lakes and lockshores are attractive places to live and play. Clean, sparkling water, abundant wildlife, beautiful scenery, aquatic recreation, and fresh breezes all come to mind when we think of going to the lake. Despite their great value, however, lakes are fragile and ephemeral. The life cycle of a lake is a large inland body of standing water that occupies a depression in the land surface. Streams flowing into the lake carry sediment, which can fill the depression in a relatively short time, geologically speaking. Soon the lake becomes a swamp, and with time the swamp fills with more sediment and vegetation and becomes a meadow or forest with a stream flowing through it. If most lakes fill quickly with sediment, why are these bodies of water so abundant today? Most lakes exist in places that were covered by glaciers during the latest ice age. About 18,000 years ago, great continental ice sheets extended well south of the Canadian border, and mountain glaciers scoured alpine valleys as far south as New Mexico and Arizona. Similar ice sheets and alpine glaciers existed in the higher latitudes of the southern hemisphere. The glaciers created lakes in several ways. Flowing ice eroded numerous depressions in the land surface, which then filled with water. The Great Lakes of North America and the Finger Lakes of Upper New York State are examples of large lakes occupying glacially scoured depressions. The glaciers also deposited huge amounts of sediment as they melted and retreated. Some of these great piles of glacial debris formed dams across stream valleys. When the glaciers melted, streams flowed down the valleys but were blocked by the sediment dams. Many modern lakes occupy glacially dammed valleys. In addition, large blocks of ice were left behind as the glaciers receded. When these ice blocks melted, they left behind depressions called kettles, which in many cases filled with water to become Kettle Lake. Most of these glacial lakes formed within the past 10,000 to 20,000 years, and sediment is rapidly filling them. Many of the smallest such lakes have already become swamps. In the next few hundred to few thousand years, many of the remaining lakes will fill with mud. The largest, such as the Great Lakes, may continue to exist for tens of thousands of years. But the lifespans of lakes such as these are limited, and it will take another glacial episode to replace them. Lakes also form by non-glacial means. A volcanic eruption can create a crater that fills with water to form a lake, such as Crater Lake in Oregon. Oxbow lakes form in abandoned river channels. Other lakes, such as Lake Okeechobee in the Florida Everglades, form in flatlands with shallow groundwater. These types of lakes, too, fill with sediment and, as a result, exist for a limited time. A few lakes, however, form in ways that maintain their existence beyond the span of a normal lake. For example, Russia's Lake Baikal is a large, deep lake lying in a depression created by active normal faults. Although rivers pour sediment into the lake, movements of the faults repeatedly deepen the basin. As a result, the lake has existed for more than 1 million years, so long that indigenous species of seals, fish, and other animals have evolved in its ecosystem. Nutrient balance in lakes. In a deep lake, sunlight is available near the surface, but nutrients are abundant mainly on the bottom. Plankton grow poorly on the surface due to low nutrient levels there, and bottom-rooted plants cannot grow due to lack of sunlight there. Thus, deep lakes contain low concentrations of nutrients and insufficient bottom sunlight to sustain aquatic food webs that generate much biomass. The low level of biological productivity often causes these lakes to have a deep blue color that we associate with a clean, healthy lake. Such a lake is called oligotrophic, meaning poorly nourished. Oligotrophic lakes have low productivities, meaning that they sustain relatively few living organisms, although a lake of this type is attractive for recreation and can support limited numbers of large game fish. As a lake fills with sediment, it becomes shallower and sunlight reaches more and more of the lake bottom. The sunlight allows bottom-rooted plants to grow. As the plants die and rot, their litter adds nutrients to the lake water. Plankton increase in numbers, as do the numbers of fish and other organisms. The lake may become so productive that its surface is covered with a green scum of plankton or a dense mat of rooted plants. The litter from this biomass contributes to sediment filling the lake, and eventually the lake becomes a swamp. A lake of this kind, with a high nutrient supply and high level of productivity in terms of biomass, is called a eutrophic lake. Eutrophic means well-nourished. Eutrophication occurs naturally as part of the life cycle of a lake. However, the addition of nutrients in the form of sewage, fertilizer runoff, and other kinds of pollution has greatly accelerated the eutrophication of many lakes. Temperature layering and turnover in lakes. If you have ever dived into a deep lake on a summer day, you have probably discovered that the top meter or so of lake water can be much warmer than deeper water. This occurs because sunshine warms the upper layer of water, making it less dense than the cooler, deeper water. The warm, less dense water floats on the cooler, denser water. The boundary between the warm and cool layers is called the thermocline. In temperate climates, colder autumn weather cools the surface water to a temperature below that of deeper water, so that the surface water becomes more dense than the deeper water. This density difference and the effects of wind cause surface water to sink and mix with the deep water, equalizing the water temperature throughout the lake. This process is called fall turnover. In the winter, Ice floats on the surface and temperature layering develops again. In spring, as ice melts on the lake, the cold surface water again is denser than deep lake waters, and spring turnover occurs. As summer comes, the lake again develops thermal layering. This seasonal process is illustrated in Figure 11.28. Turnover in temperate lakes illustrates an important Earth system's interaction among the atmosphere, the hydrosphere, and the biosphere. During summer and winter, when the lake water is layered, bottom-dwelling organisms may use up most or all of the oxygen in deep water. At the same time, surface organisms may deplete surface waters of dissolved nutrients. However, surface water is rich in oxygen because it is in contact with the atmosphere, and deep water may be rich in nutrients because it is in contact with bottom sediment. Turnover enriches deep water with oxygen and, at the same time, supplies nutrients to the surface water. The latter effect often becomes evident in the form of an algal bloom, a sudden and obvious increase in the amount of floating green algae on a lake's surface in spring and fall. Wetlands. Wetlands are known across North America as swamps, bogs, marshes, sloughs, mudflats, and floodplains. They are regions that are water-soaked or flooded for all or part of the year. Some wetlands are wet only during exceptionally wet years and may be dry for several years at a time. Wetland ecosystems vary so greatly that the concept of a wetland defies a simple definition. All wetlands share certain properties, however, the ground is wet for at least part of the time, the soils reflect anaerobic conditions, and the vegetation consists of plants such as cattails, bulrushes, mangroves, and other species adapted to periodic flooding or water saturation. North American wetlands include all stream floodplains, frozen Arctic tundra, warm Louisiana swamps, coastal Florida mangrove swamps, boggy mountain meadows of the Rockies, and the immense swamps of interior Alaska and Canada. Wetlands are among the most biologically productive environments on Earth, are important for degrading pollutants, and serve to mitigate the effects of flooding. 2/3 of the Atlantic fish and shellfish consumed by humans rely on coastal wetlands for at least part of their life cycles. A net herd of the endangered species of both plants and animals in the United States also depend on wetlands for survival. More than 400 of the 800 species of protected migratory birds and 1/3 of all resident bird species feed, breed, and nest in wetlands. Aquatic organisms consume many pollutants and degrade them to harmless byproducts. Because these organisms abound in wetlands, the ecosystems serve as natural sewage treatment systems. Wetlands also mitigate flooding by absorbing excess water that might otherwise overrun towns and farms. When European settlers first arrived in North America, the continent had 87 million hectares of wetlands. Until relatively recently, most Americans viewed wetlands as mosquito-infested, malarial swamps occupying land that can be farmed or otherwise developed if drained or filled but otherwise is worthless. In the mid-1800s, the federal government passed legislation known as the Swampland Acts, which established an official policy for filling and draining wetlands in order to convert them to agricultural uses wherever possible. Over 250,000 square kilometers were officially identified by the acts as swampland available for reclamation. Wetlands have been lost or degraded by both humans and natural causes. Many wetlands have been drained, or their sources of water cut off, through the construction of dams or dikes. Others have been filled, logged, or mined, while the introduction of non-native invasive species or toxic levels of pollution or nutrients continues to cause widespread wetland degradation. Natural wetland loss can occur by subsidence, sea level rise, drought, and erosion by large storms. According to the U.S. Environmental Protection Agency, over the past several centuries about 900,000 square kilometers of original U.S. wetlands have been degraded or destroyed, an area larger than Texas and Oklahoma combined. California and several upper Midwestern states have lost more than 80% of their historic wetlands. Beginning in the 1960s, the importance of wetlands in water purification, flood control, and wildlife habitat began to be recognized, and since the late 1980s, federal policy has been to incur no net loss of wetlands. However, it has proven more difficult to reverse practice than policy, and the net loss of wetlands continues. For example, the U.S. Department of the Interior estimated a net loss of 25,000 hectares of wetlands between 2004 and 2009. Today, wetlands make up between 6 and 9% of the lower 48 states and as much as 60%, or about 80 million hectares, of Alaska. Preserving these wetlands along with those outside the United States will present a serious future challenge as Earth's human population continues to rise and pressure increases to develop, farm, log, or ranch these wetlands. Groundwater in most places, if you drill a hole in the ground between a few meters and 100 or so meters deep, the bottom of the hole fills with water, usually within a few minutes to a few days. The water appears even if no rain falls and no streams flow nearby. The water that seeps into the hole is groundwater, which saturates Earth's crust from a few meters to a few kilometers below the surface. Groundwater is exploited by digging wells and pumping the water to the surface. It provides drinking water for more than half of the population of North America and is a major source of water for irrigation and industry. However, deep wells and high-speed pumps now extract groundwater more rapidly than natural processes can replace it in many parts of the central and western United States. As a result, groundwater resources that have accumulated over thousands or tens of thousands of years are being permanently lost. In addition, industrial, agricultural, and domestic contaminants seep into groundwater in many parts of the world. Such pollution is often difficult to detect and expensive to clean up. Porosity and permeability. Groundwater fills small cracks and voids in soil and bedrock. The volume percentage of these open spaces, called pores, is called porosity. In unlit high-fide sand or gravel, the network of open pore spaces between the individual sediment clasts results in porosity values that usually are close to 40%. In contrast, unlit high-fide mud can have porosity values of up to 90%. The generally higher porosity of unlit high-fide mud results from several physical and chemical characteristics of very fine-grained sediment. First, the platy shape of many clay crystals and crystal aggregates creates plentiful open space between sediment particles. Second, water is attracted to silt and clay-sized particles through capillary action. Third, the polar water molecule is attracted to electrically charged surfaces of clay-sized particles. Finally, water is incorporated directly into the crystal structure of some clay minerals. Most rocks have lower porosities than loose sediment. For example, sandstone and conglomerate commonly have 5 to 30% porosity, and in some cases more. Much of this porosity is left behind from the original pore network around the sand and gravel clasts, minus that lost by compaction of the sediment during burial and that lost by the introduction of mineral cements. Pore networks in quartz-dominated sandstone and gravel can stay open during deep burial because the quartz grains provide a rigid framework that resists collapse. In some cases, quartz sandstone and conglomerate with porosity values of 15% or higher serve as conventional reservoirs for petroleum or natural gas at depths in excess of 2 miles. In contrast, at such depths, mud-dominated lithologies, mudstone and claystone in particular, are characterized by porosity values of only a few percent, remarkably lower than the very high porosity of the original unlit high-fide mud. The big loss of porosity during the lithification of mud to mudrock results mainly from compaction during burial, which collapses pore spaces as the platy clay minerals and mineral aggregates become subaligned like a collapsed house of cards on a tabletop. The growth of mineral cements between the clay and silt-sized grains fills much of the remaining pore space during the lithification of mud, while the transformation of organic matter to kerogen or kerogen to petroleum can further clog available pore space in mudrocks during deep burial. Igneous and metamorphic rocks have very low porosities unless they are fractured. Porosity indicates the amount of water that rock or soil can hold. In contrast, permeability refers to how interconnected the pore spaces are and relates to the ability of rock or soil to transmit water or any other fluid including petroleum and natural gas. Water can flow rapidly through material with high permeability, but flows slowly through a low permeability material. Most materials with high porosity also have high permeability. Sand and sandstone have numerous, relatively large, well-connected pores that allow the water to flow through the material. However, if the pores are very small, as in clay or mudstone, electrical attractions between water and soil or mineral particles retard the passage of water. Although unlit high-fide clay typically has a high number of pores that are so small and tortuous that the electrical attractions with clay particles slow the passage of water, it usually has a very low permeability and transmits water slowly. The water table and aquifers when rain falls. Much of it soaks into the ground. Water does not descend into the crust indefinitely, however. Below a depth of a few kilometers, the pressure from overlying rock closes the pores, making bedrock both non-porous and impermeable. Water accumulates above this permeability barrier, filling pores in the rock and soil. This completely wet layer of soil and bedrock above the deep, impermeable rock is called the zone of saturation. The water table is the top of the zone of saturation. The unsaturated zone, or zone of aeration, lies above the water table. In this layer, the rock or soil may be moist but is not saturated, and air occupies some or all of the pore space. If you dig into the unsaturated zone, the hole does not fill with water. However, if you dig below the water table into the zone of saturation, you have dug a well. The water level in a well is at the level of the water table. During a wet season, rain seeps into the ground to recharge the groundwater, and the water table rises. During a dry season, the water table falls. Thus, the water level in most wells fluctuates with the seasons. An aquifer is any body of rock or soil that can yield economically significant quantities of water. An aquifer must be both porous and permeable so that water flows into a well to replenish water that is pumped out. Sand and gravel, sandstone, limestone, and highly fractured bedrock of any kind make excellent aquifers. In contrast, mudstone, clay, and unfractured igneous and metamorphic rocks have low porosity and permeability, and are called aquitards. Groundwater movement. Nearly all groundwater seeps slowly through bedrock and soil. Groundwater often flows at about 4 centimeters per day, although flow rates may be much faster or slower depending on permeability. Most aquifers are like sponges through which water seeps, rather than underground pools or streams. However, groundwater can flow very rapidly through large fractures in bedrock, and in a few regions underground rivers flow through caverns. In general, the water table mimics its surrounding topography. Refer again to Figure 11.30. Groundwater flows from zones where the water table is highest toward areas where it is lowest, and so some groundwater flows roughly parallel the sloping surface of the water table toward the valley. But groundwater also flows from zones of high pressure toward zones of low pressure. Because water pressure is greatest beneath the highest part of the water table, the pressure difference forces much of the groundwater to flow downward beneath the hill, then laterally toward the valley, and finally upward beneath the lowest part of the valley, where a stream flows. This is how groundwater feeds stream flow, and why streams flow even when no rain has fallen for weeks or months. Springs and artesian wells. A spring occurs where the water table intersects the land surface and water flows or seeps onto the surface. In some places, a layer of impermeable rock or clay lies above the main water table. Porous, saturated rock or sediment above the impermeable layer can form a perched aquifer. Hillside springs often flow from perched aquifers. Springs also occur where fractured bedrock or cavern systems intersect the land surface. Figure 11.32 shows a tilted layer of permeable sandstone sandwiched between two layers of impermeable mudstone. An inclined aquifer such as the sandstone layer, bounded top and bottom by impermeable rock, is a confined aquifer. Water in the lower part of the aquifer is under pressure from the weight of water above. Therefore, if a well is drilled through the mudstone and into the sandstone, water rises in the well without being pumped. A well of this kind is called an artesian well. If pressure is sufficient, the water spurts out onto the land surface. Caverns like surface streams, groundwater is capable of eroding rock and leaving behind sedimentary deposits. Recall from Chapter 10 that rainwater reacts with atmospheric carbon dioxide to become slightly acidic and capable of dissolving limestone. A cavern forms when acidic water seeps into cracks in limestone, dissolving the rock and enlarging the cracks. Mammoth Cave in Kentucky and Carlsbad Caverns in New Mexico are two famous caverns formed in this way. Although caverns form when limestone dissolves, most caverns also contain features formed by deposition of calcite. When a solution of water, dissolved calcite, and carbon dioxide percolates through the ground, it is under pressure from water in the cracks above it. If a drop of this solution seeps into the ceiling of a cavern, the pressure decreases because the drop comes in contact with the cavern air, which is at atmospheric pressure. The high humidity of the cave prevents the water from evaporating rapidly, but the lowered pressure allows some of the carbon dioxide to escape as a gas. When the carbon dioxide escapes, the drop becomes less acidic. This decrease in acidity causes some of the dissolved calcite to precipitate as the water drips from the ceiling. Over time, a beautiful and intricate stalactite grows to hang icicle-like from the ceiling of the cave. Only a portion of the dissolved calcite precipitates as the drop seeps from the ceiling. When the drop falls to the floor, it spatters and releases more carbon dioxide. The acidity of the drop decreases further, and another minute amount of calcite precipitates. Thus, a cone-shaped stalagmite builds from the floor upward to complement the stalactite. Because stalagmites are formed by splashing water, they tend to be broader than stalactites. As the two features continue to grow, they may eventually meet and fuse together to form a column. Sinkholes. If the roof of a cavern collapses, a sinkhole forms on Earth's surface. A sinkhole can also form as limestone dissolves from the surface downward. In tropical regions, deep sinkholes formed from collapse of limestone caves can expose groundwater, resulting in a deep lake called a cenote. Each year, sinkholes cause significant economic damage as buildings, roads, and other structures undergo collapse in densely populated regions underlain by limestone. A well-documented sinkhole formed in May 1981 in Winter Park, Florida. During the initial collapse, a 3-bedroom house, half a swimming pool, and 6 Porsches in a dealer's lot all fell into the underground cavern. Within a few days, the sinkhole was 200 meters wide and 50 meters deep, and it had devoured additional buildings and roads. Although sinkholes form naturally, human activities can accelerate the process. The Winter Park sinkhole formed when the water table dropped, removing support for the ceiling of the cavern. The water table fell as a result of a severe drought augmented by excessive removal of groundwater by humans. Karst topography. An irregular landscape called karst topography forms in regions underlain by limestone and other readily soluble rocks such as halite. Caverns and sinkholes are common features. Surface streams often pour into the sinkholes and disappear into the caverns. In the area around Mammoth Cave in Kentucky, streams are given names such as Sinking Creek because of their disappearing acts. Hot springs, geysers, and geothermal energy. At numerous locations throughout the world, hot water naturally flows to the surface to produce hot springs. Most hot springs form from the heating of groundwater in one of two ways. 1. Earth's temperature increases by about 30 degrees Celsius per kilometer of depth in the upper portion of the crust. Therefore, if groundwater descends through cracks to depths of 2 to 3 kilometers, it is heated by 60 degrees Celsius to 90 degrees Celsius. The hot water or steam then can rise because it is less dense than the colder water above it. However, it is unusual for fissures to descend so deep into Earth, and this type of hot spring is uncommon. Point 2. In regions of recent volcanism, magma or hot igneous rock near the surface can heat groundwater at relatively shallow depths. Hot springs heated in this way are common throughout western North and South America because these regions have been magmatically active in the recent past and remain so today. For example, magma only a few kilometers below the surface heats the hot springs and geysers of Yellowstone National Park. Most hot springs form from water rising gently to the surface from cracks in bedrock. However, geysers violently erupt hot water and steam. Geysers form from a network of cracks and small caverns in hot underground rock. Before a geyser erupts, hot groundwater seeps into the network, where it continues to be heated by the surrounding rock. Usually, cooler water fills the network of cracks and caverns from above, while hotter water fills them from below. As the water fills the caverns, the temperature of the deepest water can rise above the boiling point. Yet this superheated water does not boil, because pressure from the overlying water keeps it from doing so. Gradually, steam bubbles form in water within shallower parts of the crack system where the pressure is lower, and these bubbles start to rise just as in a heated tea kettle. If part of the channel is constricted, the bubbles can accumulate there, forming a temporary barrier that allows the steam pressure below to increase in a manner similar to a pressure cooker. The rising pressure eventually forces some of the bubbles upward past the constriction, pushing water out of the geyser vent and lowering the pressure on the superheated water below the constriction. Because it is already above the boiling point, the superheated water suddenly flashes to stream, forcing hot water and steam skyward past the constriction and out of the geyser's vent during the main eruption. Eventually, an insufficient volume of superheated water remains in the crack system to sustain the eruption, and it stops. The most famous geyser in North America is Old Faithful in Yellowstone National Park, which erupts on the average of once every 91 minutes. Old Faithful is not as regular as people like to believe. The intervals between eruptions can vary from about 45 to 125 minutes. These variations in the eruptive interval are caused by the year-to-year changes in the volume of water available to fill the crack system as well as seasonal changes in the temperature of water infiltrating the crack system from the surface. In addition, changes in the eruptive behavior of geysers such as Old Faithful can be caused by earthquakes. As seismic waves pass through rocks forming a geyser's plumbing system, its shape can change as rocks or sediment are dislodged. Hot groundwater can be used to drive turbines and generate electricity, or it can be used directly to heat homes and other buildings. Energy extracted from Earth's heat is called geothermal energy. In 2013, 64 geothermal plants, mostly in California and Nevada, were operating in the United States. These produced a generating capacity of about 2,700 megawatts, enough to supply about 3 million people with electricity. Unfortunately, compared with the potential of geothermal as a source of energy in the United States, the current generating capacity is minuscule. By the end of 2013, the most recent data available from the International Energy Agency, only about 0.4% of U.S. electricity was generated by geothermal sources. In an effort to make the development of additional geothermal areas more economic, some developers are constructing enhanced geothermal systems in which permeability in rock that is already hot is increased through drilling and hydraulic fracturing. The first commercial-scale enhanced geothermal system in the United States is the Desert East Pilot Project, which began operating in 2013. Chapter 12: Water Resources. Introduction. More than two-thirds of Earth's surface is covered with water. But most of this water is salty, and most of the fresh water is frozen into the Antarctic and Greenland ice caps. Humans divert half of all the flowing water from rain and snow that falls on the continents, but even that is not enough for our burgeoning population and per capita consumption. Today, as we reach, and in some cases exceed, the limits of our water resources, the well indeed is running dry. Currently about one-fifth of the world's population lives in a region of water scarcity in which the aggregate demand by all sectors exceeds that available. Under the existing climate change scenario, the United Nations has projected that by the year 2030, water scarcity is expected to affect half the world's population and displace between 24 million and 700 million people. Not only will water scarcity increase future levels of human poverty, but it also may lead to armed conflict as the competition for the dwindling resource increases. An important aspect of water scarcity is water quality. In addition to being physically scarce in some regions, much of the surface water and groundwater in industrial areas is heavily polluted, destroying natural habitats and making the resource less useful for humans. Water supply and demand. Rain and snow continuously replenish freshwater on land, so that the amount of available freshwater is about the same as it was 2 centuries ago. But the demand for water has risen dramatically, until it has approached or exceeded supply in many parts of the world. In the early 1800s, there were 1 billion people on Earth, now there are over 7 billion. Thus, as the human population has grown, the amount of available freshwater per person has diminished. In addition, our technological society uses water at rates that would have been inconceivable to Ben Franklin. Water use falls into 2 categories. Any process that uses water and then returns it to Earth locally is called withdrawal. Most of the water used by industry and homes is returned to streams or groundwater reservoirs near the place from which it was taken. For example, river water pumped through an electric power generating station to cool the exhaust is returned almost immediately to the river. Water used to flush a toilet in a city is pumped to a sewage treatment plant, purified, and discharged into a nearby stream. In contrast, a process that uses water and then returns it to Earth far from its source is called consumption. Most irrigation water evaporates, disperses with the wind, and returns to Earth as precipitation hundreds or thousands of kilometers from its source. Although industry accounts for about half of all water withdrawn in the United States, agriculture accounts for most of the water that is consumed and not returned to its place of origin. Globally, about 2/3 of the total water that is withdrawn is consumed. Water use is subdivided into domestic, industrial, and agricultural categories. According to the U.S. Geological Survey, by far the largest users of water in the United States are power plants, which in 2015 accounted for about 41% of total water withdrawals, and irrigation for agriculture, which accounts for about 38% of total consumption. The specific categories for which the water is used varies by state, with the arid western states consuming more water for irrigation and the more populous eastern states using more water for thermoelectric power. Figure 12.5 shows the total freshwater withdrawals by source from 1950 through 2015, plotted alongside U.S. population. Although the U.S. consumes an extravagant volume of water by global standards, total water withdrawals fell between 2010 and 2015. The drop in total withdrawals was primarily caused by decreases in withdrawals for thermoelectric power, which accounted for 89% of the decrease in total withdrawals, and public supply withdrawals, which accounted for another 9% of the decline. Partially offsetting these reductions in water consumption were increases in withdrawals for irrigation and mining. Domestic water use. The average American household uses about 1,100 liters per day, many times the amount needed to maintain a healthy life, although average consumption per household varies significantly by region. Households located in arid regions commonly use more than twice as much water as households located in humid regions, mainly because of differences in landscape irrigation, particularly lawns. These differences in average household water use among the different states are compounded by the fact that many of the states experiencing recent large population increases are also states in which the arid climate leads to higher average household consumption. As the arid western states have become more populated, domestic water conservation practices have become more commonplace, leading to a decrease in overall average household consumption between 2005 and 2015. Figure 12.7 shows typical volumes of water used in a variety of domestic activities in the United States and tips for reducing this volume. Although greater water awareness has reduced the average U.S. household consumption since 2005, it is important to keep in mind that domestic use accounts for only about 12% of the water used in the United States. In contrast to the comparatively extravagant per capita water usage in the United States, the World Health Organization defines reasonable water access in less developed agricultural societies as 20 liters of sanitary water per person per day, assuming that the source is less than 1 kilometer from the home. Yet 1.1 billion people, about 1/6 of the global population, lack even this small amount of clean water. Water access can fall short for three reasons: either there isn't enough water, the water is unfit to drink, or the source is so far away that people must carry their water long distances from public wells or streams to their homes. The World Health Organization estimates that diarrheal illnesses caused by unsafe water account for 4.1% of global disease and are responsible for the deaths of 1.8 million people each year, most of them children under age 5. Industrial water use. The cooling systems in electric power generating plants account for roughly 45% used each day in the United States. Although much of this water is returned to the stream from which it was taken, it is considerably warmer, which, as we shall see, affects aquatic ecosystems. As a result, in March of 2011, the U.S. Environmental Protection Agency issued proposed standards for closed-cycle cooling systems utilizing cooling towers that release heat through evaporation. Whether or not these proposed standards become reality remains to be seen, however. Besides use by power plants, all other industrial needs add an additional 10% to the national water demand. The quantities of water required to produce some common industrial products are shown in Figure 12.8. Agricultural water use. In 2010, agriculture accounted for 32.5% of total water use in the United States and 76% of all fresh groundwater withdrawals. Figure 12.9 shows that different agricultural products use vastly different amounts of water. California's Central Valley was once a desert, but irrigation has transformed it into an immensely productive region for growing fruits and vegetables. The productivity of the Great Plains in the western United States would decline by net herd to 1/2 if irrigation were to cease. Globally, many nations rely on irrigation for more than half of their food production. Estimates vary, but roughly 70% of all global water consumption is used to irrigate crops. In dry regions, most if not all farmland must be irrigated, and as a result, both surface and groundwater resources are stressed, leading to a higher risk of insufficient water availability. Dams and diversion. Much of Earth's rain falls in the wrong places or at the wrong times to be of much use to humans. For thousands of years, people realized that the problem could be ameliorated by building dams to store water that falls at the wrong time and by diverting water that falls in the wrong places. For example, the Tigris and Euphrates rivers flow through deserts of the Middle East from distant mountains, but ancient Babylonians farmed the desert by irrigating the parched lowlands with diverted river water. In modern times, engineers build huge dams to store water. In 1950, there were 5,700 large dams in the world. As of 2018, there are about 57,000. Almost half of the new dams were built in China. This unprecedented building boom has increased water availability in many regions and produced large amounts of hydroelectric energy, but as we will see in the discussion that follows, these benefits are offset against significant human and environmental costs. In many regions, surface water is scarce, but huge reservoirs of groundwater are accessible beneath the surface. This groundwater can be pumped to the surface for human use. The United States receives about 3 times more water from precipitation than it uses. However, some of the driest regions are those that use the greatest amounts of water. For example, some of the most productive agricultural regions are located in the deserts of California, Texas, and Arizona, where crops are entirely supported by irrigation. Desert cities such as Phoenix, Los Angeles, Albuquerque, and Tucson support large populations that use hundreds of times more water than is locally available and renewable. Surface water diversion. A diversion system is a pipe or canal constructed to transport water. Many of these systems use gravity to move the water, while others use pumps to lift water uphill. Diversion systems are often augmented by dams that store water. Dams are especially useful in regions of seasonal rainfall. For example, in the arid and semi-arid western United States, much of the annual precipitation occurs in winter and spring. Dams store this water for the summer irrigation season, when crops need it. In addition, the potential energy of the water in a reservoir can generate electricity, and because reservoirs can refill with water, hydroelectric power is renewable. In 2016, hydroelectric power from dams accounts for about 16% of total global electricity consumption. Thus, dams are beneficial, but they also can create numerous undesirable effects, described next. Loss of water. The reservoir formed by a dam provides more surface area for evaporation and more bottom area for seepage into bedrock than did the stream that preceded it. Therefore, less total water flows downstream. In addition, many canals built to carry water from a reservoir to farmland are simply ditches excavated in soil or bedrock, and they leak profusely. Salinization. As described in Chapter 11, all streams contain a dissolved load, ions derived from continental weathering and dissolved in a stream. When farmers use river water to irrigate cropland, the water evaporates, leaving the ions behind to form various salts in the soil. If desert or semi-desert soils are irrigated for long periods of time, salt accumulates and lowers the soil fertility. In the United States, salinization lowers crop yields on 25 to 30% of irrigated farmland, more than 50,000 square kilometers, an area roughly the size of Vermont and New Hampshire combined. The problem is particularly acute in the San Joaquin and Imperial Valleys of Southern California. Globally, salinization affects between 10 and 20% of irrigated land, some 250,000 square kilometers or about the size of Wyoming, and it is increasing at a rate of roughly 6% per year. Silting. A stream deposits its sediment in a reservoir, where the current slows. Rates of sediment accumulation in reservoirs vary with the sediment load of the dammed river. Lake Mead, impounded behind Hoover Dam on the Colorado River in Arizona and Nevada, lost 6% of its capacity in its first 35 years as a result of sediment accumulation. At such a rate, a reservoir lasts for hundreds of years, providing a considerable societal resource in terms of power generation, water storage, and recreation. However, in a few other instances, engineers have made expensive miscalculations of sedimentation rates that have greatly shortened the lifespan of reservoirs. The Tarbala Dam in Pakistan was completed in 1978 after 9 years of construction, and by 2005, it was already more than 25% filled with silt. The reservoir behind the Sanmengxia Dam on the Yellow River in China filled 4 years after the dam was finished, making both the dam and reservoir useless. In 1907, Milltown Dam in western Montana was built to supply local hydroelectric power, but the very next year the reservoir above the dam nearly filled with mine tailings washed in from a large flood. The tailings not only greatly reduced the capacity of the dam to produce hydroelectric power, but they also formed a concentration of heavy metals that polluted groundwater in the area. Erosion. Sediment trapping by dams also can significantly impact the hydrology and ecology of areas downstream that had received sediment during per-dam floods. Recently, the beaches along the Colorado River in the Grand Canyon were disappearing rapidly because management practices at the Glen Canyon Dam upstream prevented flooding in the Grand Canyon. In a similar way, beaches are vanishing from many other dammed streams. A classic example of the way dams affect the movement of sediment has occurred in the Colorado River within the Grand Canyon, located directly below the Glen Canyon Dam. Once the dam was built in 1963, all of the sandy sediment being transported downstream in the Colorado River was deposited in Glen Canyon Reservoir. The only sand delivered to the Colorado within Grand Canyon came from tributaries that entered the river below the dam. Between 1963 and 1991, this reduction in sand delivery caused sandbars and beaches within the Grand Canyon to erode, not only reducing the availability of prime camping spots within the park but greatly limiting the availability of shallow, slow-flowing aquatic environments critical to the survival of fish. In addition, the lack of floods promoted the widespread establishment of tamarix, a non-native plant that colonized the river banks and further disrupted the river ecosystem. In the spring of 1996, and again in the fall of 2004 and spring of 2008, scientists released enough water from Glen Canyon Dam to create a flood in the Grand Canyon. These high-flow experiments were designed to mimic the effects of pre-dam flooding on the Colorado River and investigate whether such floods could help rebuild sandbars, benefit aquatic organisms, and limit the spread of tamarix. The first flood in 1996 eroded sediment from existing sandbars and moved it to higher elevations, but it did not move much sand from the river bed to the sandbars as was hoped. In response, the 2004 and 2008 floods were strategically timed to coincide with tributary floods that brought new sand into the Colorado. These floods succeeded in moving much of the newly delivered sand from tributaries onto the banks and sandbars in the Colorado, causing them to enlarge. Research conducted on long-term study sites in the Grand Canyon showed that 75% of the sandbars grew over the course of the 3 artificial floods. In addition, the spring releases in 1996 and 2008 showed that these floods helped reduce the spread of tamarix not only by partially removing existing plants but also by reducing the establishment of new tamarix seedlings because the spring releases came before the plants went to seed. Lastly, the spring floods were found to increase the density of small aquatic invertebrates, especially insects, that are an important food source for fish. Along with the greater availability of shallow water, slow-flowing environments, the increases in aquatic invertebrates following the floods contributed to increasing the population of rainbow trout, an important fishery below the dam, by 800%. Because a reservoir accumulates silt and sand, it also interrupts the supply of sediment to the seacoast, causing some coastal beaches to erode faster than new sand can be delivered by natural processes. This problem has led to expensive sand replenishment projects on some popular beaches in the eastern United States. Risk of disaster: a dam can break, creating a disaster in the downstream floodplain. One of the greatest floods since the last ice age roared down Idaho's Teton River Canyon when the Teton Dam failed on June 5, 1976. The Teton Dam failed because of deficiencies in the design of the dam foundation, construction shortcuts, lack of a low-fill spillway, and rapid initial filling of the reservoir. In particular, the Teton Dam was built on a foundation of highly permeable bedrock, and this bedrock was insufficiently filled with grout prior to construction of the dam. In addition, one of the dam abutments was not sealed against the bedrock, and the dam core was not completely grouted. The reservoir behind the Teton Dam was first filled in the spring of 1976, and it filled more quickly than expected due to rapid melting of snow in the drainage basin. On June 5, 1976, clear water was observed leaking through the dam foundation and subsequently through ungrouted joints in the bedrock adjacent to the dam abutments. Within a matter of hours, the leaking water became muddy, indicating that internal erosion of the dam itself was beginning to occur, and a sinkhole developed on the downstream side of the dam and began to flow additional muddy water. Although workers attempted to plug the sinkhole with large boulders, it quickly enlarged and propagated to the top of the dam, causing a breach. As reservoir water poured through the breach, it quickly enlarged and led to draining of the entire contents of the reservoir. Although a low-elevation spillway had been designed for controlled lowering of the reservoir, construction delays prevented it from being operational when the reservoir was first filled that spring. Without the spillway, there was no way to fill the reservoir slowly or prevent it from filling to capacity. Within hours, the entire contents of the Teton Reservoir emptied, inundating about 300 square miles with floodwater and traveling over 150 miles downstream. Floodwaters swept away 154 of the 155 buildings in the town of Wilford, 6 miles below the dam. The town no longer exists. The flood inundated the lower half of Rexburg, a larger town farther downstream, damaging or destroying 4,000 homes and 350 businesses. Damages totaled about $400 million. Only 11 people died because civil authorities warned and evacuated most of the people. But if the flood had occurred in the middle of the night when warnings and evacuations would have been more difficult, thousands might have been killed. Recreational and aesthetic impacts. Dams are often built across narrow canyons to minimize engineering and construction costs. But when the canyon upstream of the dam is flooded, unique scenery and ecosystems are destroyed. Glen Canyon Dam on the Colorado River created Lake Powell by flooding one of the most spectacular desert canyons in the American West. Today, Glen Canyon is submerged for more than 300 kilometers above the dam and can be seen only in old photos. Although these environments are now effectively gone, the creation of Lake Powell provides new opportunities for fishing and other water sports that did not exist prior to construction of Glen Canyon Dam. Disputes often arise among various groups that use water in dammed reservoirs. To prevent flooding, a reservoir should be nearly empty by spring so that it can store water and fill during spring runoff. Thus, a reservoir should be drawn down slowly during summer and fall. Agricultural runoff and supplied for irrigation during summer months. However, recreational users object to a lowering of reservoir levels during summer, when they visit reservoirs most frequently. Managers of hydroelectric dams prefer to run water through their turbines during times of peak demand for electricity, which rarely correspond to flood management, irrigation, or recreational schedules. Ecological disruptions. A river is an integral part of the ecosystem that it flows through, and when the river is altered, the ecosystem changes. Dams interrupt water flow during portions of the year, prevent flooding, change the temperature of the downstream water, and often create unnatural daily fluctuations in stream flow. All of these changes alter relative abundances of aquatic and riparian species and may create specific ecological problems in individual rivers. For example, before Egypt's Aswan Dam was built, the Nile River flooded every spring, depositing nutrient-rich sediment over the floodplain and delta. When the dam and reservoir cut off the silt supply, however, erosion of the delta front by the sea caused the Nile Delta to shrink. In addition, the loss of an annual supply of nutrients eliminated a source of free fertilizer for floodplain farms. Although the energy produced by the dam is used to manufacture commercial fertilizers, many of the poorer farmers on the floodplain cannot afford to purchase what the river once provided for free. Human costs. In the past 50 years, as many as 80 million people globally, approximately equal to 26% of the U.S. population, have been forcibly removed from their homes and farms to make way for the reservoirs behind dams. When these people moved into the relocation areas, they impacted the lives of the people already living there. Additionally, in many regions waterborne diseases become more prevalent surrounding stagnant water impounded behind a dam than they were near free-flowing streams that existed prior to the dam. Construction of the Three Gorges Dam in China, the largest hydroelectric dam in the world, has forced the relocation of about 1.4 million people. Roughly 300,000 more than originally anticipated were relocated because the rise and fall of the immense reservoir has triggered landslides along its banks, while the slower flow has caused harmful pollutants to accumulate. Dam removal. Although dams continue to provide an indispensable source of hydroelectric power along with water for agriculture and recreation, the societal risks and environmental costs of dams has significantly reduced the rate of new dam construction in the United States over the past 50 years. In fact, hundreds of dams have been removed in the United States in recent years, in part because of the expense required to maintain the aging structures and in part because of the rapidly growing interest in river restoration. In 2017, for example, a total of 86 dams were removed in the United States, reconnecting over 550 miles of river. Between 1912 and 2017, a total of 1,492 dams were removed. Although few new dams are being constructed presently in the United States and the removal of dams is accelerating, this trend is largely restricted to the United States. Elsewhere around the globe, a major new initiative in hydroelectric power generation is underway in an effort to bring reliable electricity to more people. As of 2014, at least 3,700 new large dams with at least 1 megawatt of electricity capacity were either planned or were under construction, primarily in countries with emerging economies. The new dams are projected to increase the global capacity of hydroelectric power by 73% or more, but even this dramatic increase in generation capacity will fail to keep up with projected increase in electricity demand. In addition, the construction of new dams outside the United States is projected to reduce the number of large, free-flowing rivers by 21% and significantly reduce freshwater biodiversity. Thus, although the construction of large dams for hydropower historically has been viewed as a sign of human progress, these benefits are offset and may be ultimately outweighed by the negative impacts of dams on river ecosystems, the displacement of humans, and the alteration of regional water balances across watersheds. Groundwater diversion. Groundwater provides drinking water for more than half of the population of North America and is a major source of water for irrigation and industry. It is a valuable resource because, 1. It is abundant, 60 times more freshwater exists underground than in streams and lakes combined. 2. Groundwater moves very slowly and remains available during dry periods. 3. In some regions, groundwater flows from wet environments to arid ones, providing a source of water in dry areas. Groundwater depletion. If groundwater is pumped to the surface faster than it can flow through the aquifer to the well, the water table forms a cone of depression surrounding the well. When the pump is turned off, groundwater flows back toward the well, typically in a matter of days or weeks if the aquifer has good permeability, and the cone of depression disappears. Conversely, if water is continuously removed more rapidly than it can flow to the well through the aquifer, the water table drops. Before the development of advanced drilling and pumping technologies, the human impact on groundwater was minimal. Today, however, deep wells and high-speed pumps can extract groundwater more rapidly than it is recharged. Where such excessive pumping is practiced, the water table falls as the groundwater reservoir becomes depleted. In some cases, the aquifer is no longer able to supply enough water to support the farms or cities that have overexploited it. This situation is common in the central, western, and southwestern United States and is becoming more common along the eastern coastal plain. The Ogallala Aquifer extends almost 900 kilometers from the Rocky Mountains eastward across the prairie, and from Texas to South Dakota, figure 12.21. It consists of water-saturated porous sandstone and conglomerate deposited as sediment shed eastward off the southern Rocky Mountains, mostly between 6 and 2 million years ago. The aquifer averages about 65 meters in thickness. Its upper surface, the water table, ranges in depth from zero where the aquifer recharges surface streams to about 150 meters. The Ogallala is the world's largest known aquifer and has been heavily exploited since the 1930s. About 200,000 wells were drilled into the aquifer between 1930 and 2000, and extensive irrigation systems were installed throughout the region. Today, the Ogallala Aquifer supplies roughly 30% of all groundwater pumped for irrigation in the United States. Prior to development, the total volume of the Ogallala Aquifer was about 3,800 cubic kilometers of water, more than exists in Lake Huron and enough to cover the entire lower 48 U.S. landmass with about a half meter of water. Most of the aquifer's water accumulated when the last Pleistocene ice sheet melted, about 15,000 years ago. However, today the high plains receive little rain, and the aquifer is mostly recharged by rain and snowmelt from the southern Rocky Mountains, hundreds of kilometers to the west. The problem is that the rate of consumption of groundwater from the Ogallala Aquifer is much greater than the rate of recharge from all combined sources. Not only is the total volume of precipitation across the recharge area for the Ogallala Aquifer far smaller than the volume of water formerly available from melting of Pleistocene glaciers, but water moves very slowly through the aquifer, at an average rate of only about 15 meters per year. At this rate, groundwater takes 60,000 years to travel from the southern Rocky Mountains to the eastern edge of the aquifer. Presently, approximately 9.6 billion liters are returned to the aquifer every year through rainfall and groundwater flow. However, farmers remove nearly 10 times this volume annually. Under such conditions, the deep groundwater is, for all practical purposes, non-renewable. Indeed, in some of the drier regions of northwest Texas and west-central Kansas, wells drilled into the Ogallala Aquifer already are depleted. If the present pattern of water use continues, 1/4 of the original water in the Ogallala Aquifer will be consumed by 2020. Depletion of the Ogallala Aquifer has serious economic consequences. About 20% of the total U.S. agricultural output, including 40% of the feedlot beef, is produced by water from the aquifer, with a total value of $32 billion. If the aquifer is depleted and another source of irrigation water is not found, productivity in the Central High Plains is expected to decline by 80%. Farmers will go bankrupt, and food prices will rise throughout the nation. Subsidence. Excessive removal of groundwater can cause subsidence, the sinking or settling of Earth's surface. When water is withdrawn from an aquifer, pore spaces that had been filled with water collapse. As a result, the volume of the aquifer decreases and the overlying ground subsides. In the aquifer underlying the San Joaquin Valley of California, the estimated reduction in water storage capacity by groundwater withdrawal is equal to about 40% of the total capacity of all surface reservoirs in the state. Subsidence rates can reach 5 to 10 centimeters per year, depending on the rate of pumping and the nature of the aquifer. Some areas in the San Joaquin Valley have sunk nearly 10 meters. The land surface has subsided by as much as 3 meters in the Houston-Galveston area of Texas. The problem is particularly severe in cities. For example, Mexico City is built on an old lake bottom. Over the years, as the weight of buildings and roadways has increased and much of the groundwater has been removed, parts of the city have settled as much as 8.5 meters. Many millions of dollars have been spent to maintain the city on its unstable base. Similar problems are affecting Phoenix, Arizona, and other U.S. cities. Unfortunately, subsidence is irreversible. Once groundwater is withdrawn and an aquifer compacts, porosity is permanently lost so that groundwater reserves cannot be completely recharged, even if water becomes abundant again. Saltwater intrusion. 2 types of groundwater occur in coastal areas: fresh groundwater and salty groundwater that seeps in from the sea. Freshwater floats on top of salty water because it is less dense. If too much freshwater is removed from an aquifer, salty groundwater that is unfit for drinking, irrigation, or industrial use rises to the level of wells. Saltwater intrusion has affected much of South Florida's coastal groundwater reservoirs. Once an area is contaminated by saltwater intrusion, it dramatically reduces freshwater storage in that aquifer. The Great American Desert. In the years following the Civil War, an American geologist, John Wesley Powell, explored the area between the Western Mountains and the 100 degrees meridian. He recognized that most of this region is arid or semi-arid, and he called it the Great American Desert. Despite Powell's warning about inadequate water, Americans flocked to settle there. Several parts of this region now use huge amounts of water for cities, industry, and agriculture, although they receive little precipitation. Some desert cities, including Phoenix, El Paso, Reno, and Las Vegas, rely on diversion of surface water and/or overpumping of groundwater for nearly all of their water. Billions of dollars have been spent on projects to divert rivers and pump groundwater to serve this area of the country. In California alone, the 2 largest irrigation projects in the world have been built, along with 1,400 dams. More than 80% of the water diverted to Southern California is used to irrigate desert and near-desert cropland. The water supplied to these farms commonly irrigates crops such as cotton, rice, and alfalfa. Cotton fields require 17,500 liters of water per kilogram of cotton product. Rice and alfalfa also use great amounts of water. The U.S. government pays large subsidies to farmers in naturally wet southeastern and south-central states not to grow those same crops. The irrigation water used to support cattle ranching and other livestock in California is enough to supply the needs of the entire human population of the state. Controversy over water diversion projects is not limited to the American West. New York City obtains much of its water from reservoirs in upstate New York, and the New York City Board of Water Supply controls those reservoirs and watersheds hundreds of miles from the city. Opposing interests of local land use groups and city water users have provoked heated conflicts in the state. The Colorado River. The Colorado River runs through the southwestern portion of the Great American Desert. Starting from the snowy mountains of Colorado, Wyoming, Utah, and New Mexico, it flows across the arid Colorado Plateau and southward into Mexico, where it empties into the Gulf of California. Because the river flows through a desert, farmers, ranchers, cities, and industrial users along the entire length of the river compete for rights to use the water. In the 1920s, the Colorado River discharged 18 billion cubic meters of water per year into the Gulf of California. In 1922, the U.S. government apportioned 9 billion cubic meters for the river's upper basin and the remaining 9 billion cubic meters for lower basin users in Arizona, California, and Nevada. Thus, all the water was allocated and none of it was set aside for maintenance of the river ecosystem or for Mexican users south of the border. No water flowed into the sea. In 1944, an international treaty awarded Mexico 1.5 billion cubic meters of water via the Colorado River, less than 1/10 of the annual volume that had been flowing into the Gulf of California 20 years earlier. Half of this amount was to be taken from the upper Colorado River basin, and half from the lower basin. In 2001, the U.S. government passed legislation specifying how water surpluses within the Colorado River basin should be shared among the states involved, but did not set aside any surplus water for Mexico. These collective actions created hard feeling among Mexicans living along the lower Colorado River toward U.S. management of river water north of the border. Finally, in 2012, the U.S. government passed legislation that included Mexico among the list recipients of surplus Colorado River water stored in U.S. reservoirs. In return, Mexico agreed to cut down on its use of Colorado River water during periods of drought. In addition to the challenge of equitably providing enough water from the Colorado River to sustain the environment and meet human demand on both sides of the international border is the challenge of maintaining the quality of the water along the length of the river. The Colorado and many of its tributaries flow across sedimentary rocks, many of which contain soluble salt deposits. As a result, the Colorado is a naturally salty river. In addition, the U.S. government built 10 large dams on the Colorado, and evaporation from the reservoirs has further concentrated the salty water. In 1961, the water flowing into Mexico contained 27,000 ppm dissolved salts, compared with an average salinity of about 100 ppm for large rivers. For comparison, 27,000 ppm is 77% as salty as seawater. Mexican farmers used this water for irrigation, and their crops died. In 1973, the U.S. government built a desalination plant to reduce the salinity of Mexico's share of the water. There are also significant questions about the possibility of a long-term drought in the Southwest. Tree ring studies have shown that more extreme and extended droughts have occurred in the past several centuries than have been experienced in modern times. With current demands on the Colorado River increasing, even a minor drought can have severe consequences. The end of 2004 marked 5 consecutive years of lower-than-average rainfall and subsequent decline in reservoir levels. In January 2005, Lake Powell was at 35% of its capacity, the lowest level since 1969, when the reservoir was being filled. Some of this water since has been replenished, but as of August 2018, the reservoir was only at 48.3% of capacity. Inflows over the past water year were only about 50% of normal, whereas outflows required by treaty were about 96% of normal for the past water year. Clearly, maintaining a reliable supply of water for the growing population of the Colorado River Basin is one of the most challenging public policy issues of the Southwest. Water and international politics. The Jordan River flows along the border between Israel and its longtime adversaries, Jordan and Syria. In the north, it forms the boundary between Israel and the disputed Golan Heights, and downstream it forms the boundary between Israel and the disputed West Bank. Population in the water-parched Jordan River Basin was about 44 million in 2011 and is expected to increase to about 73 million by 2050. Compounding the region's political tensions is the fact that nearly all of the renewable surface water runoff is being used and groundwater systems are being pumped at levels that are not sustainable, causing local saltwater intrusion in some of the coastal areas. Additional tensions related to water resources are caused by planned or actual construction of dams on tributaries of the Jordan River that alter the volume of water flowing down the river. In addition, a large volume of water is diverted into irrigation projects in Israel, further decreasing the amount available to Jordan and Syria. Pollution of the very limited surface water and groundwater supplies has led to additional conflict. Current international water law offers little help in resolving conflicts over water. In general, downstream nations argue that a river or aquifer is a communal resource to be shared equitably among all adjacent nations. Predictably, many upstream nations maintain that they have absolute control over the fate of water within their borders and have no responsibility to downstream neighbors. Any international code of water use must be based on 3 fundamental principles. 1. Water users in one country must not cause major harm to water users in other countries downstream. 2. Water users in one country must inform neighbors of actions that may affect them before the actions are taken. 3. People must distribute water equitably from a shared river basin. Unfortunately, these principles, especially the last one, are open to such subjective and self-interested interpretations that their intent is easily and often subverted. Despite these political challenges, since the 1950s more than 200 agreements have been developed to address issues of water management between individual nations, and these agreements cover issues of flood control, hydropower projects, or allocations for consumptive or non-consumptive uses. Although these are promising developments, many of the agreements specify allocations in fixed amounts, thereby ignoring annual variability in precipitation and changing needs. Water pollution while consumption reduces the quantity of water in a stream, lake, or groundwater reserve. Pollution is the reduction of the quality of the water by the introduction of impurities. A polluted stream may run full to the banks, yet it may be toxic to aquatic wildlife and unfit for human use. In the early days of the Industrial Revolution, factories and sewage lines dumped untreated wastes into rivers. As the population grew and industry expanded, many of our waterways became fetid, foul-smelling, and unhealthy. The first sewage treatment plant in the United States was built in Washington, D.C., in 1889, more than 100 years after the Revolutionary War. Soon other cities followed suit, but few laws regulated industrial waste discharge. In 1952 and again in 1969, the Cuyahoga River in Cleveland, Ohio, was so heavily polluted with oil and industrial chemicals that it caught fire, spreading flames and smoke across the water. While the highly publicized photographs of the flaming river flowing through downtown Cleveland had a powerful visual impact, other water pollution disasters were insidious, such as that of Love Canal in New York State, discussed below. These and similar incidents made it clear that water pollution was endangering health and reducing the quality of life for people throughout the United States. As a result, Congress passed the Clean Water Act in 1972. The legislation states that, 1. It is the national goal that the discharge of pollutants into the navigable waters be eliminated by 1985. 2. It is the national goal that, wherever attainable, an interim goal of water quality which provides for the protection and propagation of fish, shellfish, and wildlife and provides for recreation in and on the water be achieved by July 1, 1983. 3. It is the national policy that the discharge of toxic pollutants in toxic amounts be prohibited. Types of pollutants. Water pollutants have different levels of toxicity to humans and the environment. In addition, some pollutants are easier and less expensive to remove or stabilize than others, depending on the physical and chemical nature of the pollutant itself. Of particular importance is whether or not a pollutant can be removed through the metabolic actions of bacteria that either already exists or else are introduced into the polluted water as part of a cleanup operation. Biodegradable pollutants. A biodegradable material is one that decays naturally, being consumed or destroyed in a reasonable amount of time by organisms that live in soil and water. Several types of contaminants are biodegradable pollutants. 1. Sewage is wastewater from toilets and other household drains. It includes biodegradable organic material such as human and food wastes, soaps, and detergents. Sewage also includes some non-biodegradable chemicals because people often flush paints, solvents, pesticides, and other chemicals down the drain. 2. Disease organisms, such as typhoid and cholera, are carried into waterways in the sewage of infected people. 3. Phosphates and nitrate fertilizers flow into surface water and groundwater mainly from agricultural runoff. Phosphate detergents as well as phosphates and nitrates from feedlots also fall into this category. Non-biodegradable pollutants. Many materials are not decomposed naturally by environmental chemicals or consumed by decay organisms, and therefore they are non-biodegradable. Not all of these are poisons, but some are. Non-biodegradable poisons are called persistent bioaccumulative toxic chemicals. The Environmental Protection Agency recognizes tens of thousands of PBTs. Yet even non-toxic materials can pollute and adversely affect ecosystems. Non-biodegradable pollutants can be roughly subdivided into three broad categories. 1. Many organic industrial compounds are particularly troublesome because they are toxic in high doses, are suspected carcinogens in low doses, and can survive for decades in aquatic systems. Examples include some pesticides, dioxin, and polychlorinated biphenyl compounds, commonly referred to as PCBs. 2. Toxic inorganic compounds include mine wastes, road salt, and dissolved ions such as those of cadmium, arsenic, and lead. 3. When sediment enters surface waters, it neither fertilizes nor poisons the aquatic system. However, the sediment muddies streams and buries aquatic habitats, thus degrading the quality of an ecosystem. Radioactive materials include wastes from nuclear power plants, nuclear weapons, the mining of radioactive ores, and medical and scientific applications. Heat can also pollute water. In a fossil fuel or nuclear electric generator, an energy source boils water to form steam. The steam runs a generator to produce electricity. The exhaust steam must then be cooled to maintain efficient operation. The cheapest cooling agent is often river or ocean water. A 1,000 megawatt power plant heats 10 million liters of water by 35 degrees Celsius every hour. The warm water can kill fish directly, affect their reproductive cycles, and change the aquatic ecosystems to eliminate some native species and favor the introduction of new species. For example, if water is heated, indigenous cold water species such as trout will die out and be replaced by carp or other warm water fish. Any of these categories of pollutants can be released in either of two ways. Point source pollution arises from a specific site such as a septic tank, a gasoline spill, or a factory. In contrast, non-point source pollution is generated over a broad area. Fertilizer and pesticide runoff from lawns and farms falls into this latter category. How sewage, detergents, and fertilizers pollute waterways. Recall from Chapter 11 that an oligotrophic stream or lake contains few nutrients and clear, nearly pure water. Sewage, detergents, and agricultural fertilizers are plant nutrients. They do not poison aquatic systems, they nourish them. If humans dump one or more of these nutrients into an oligotrophic waterway, aquatic organisms multiply so quickly that they consume most of the dissolved oxygen. Many fish, such as trout and salmon, die. Other organisms, such as algae, carp, and water worms, can proliferate. Thus, an increased supply of nutrients can transform a clear, sparkling stream or lake into a slime-covered, eutrophic waterway. If humans release even more sewage, detergent, or fertilizer, decay organisms multiply so rapidly that they consume all the oxygen. As a result, most aquatic life dies. Then, anaerobic bacteria take over, releasing noxious hydrogen sulfide gas that bubbles to the surface and smells like rotten eggs. When raw sewage consisting of human waste is discharged into a stream, decay organisms immediately begin to break it down. At the same time, the current carries the sewage and decay organisms downstream. Over time, the organisms consume the waste and they eventually die off when their food supply is consumed. Natural turbulence replenishes oxygen in the water and fully aerobic organisms become re-established. Thus, the river cleanses itself. However, if the original source of sewage is too large, or if every town along the river dumps sewage into the same waterway, then these natural cleaning mechanisms become overwhelmed and the river remains polluted all the way to the sea. Moreover, many sewage treatment plants ultimately release the treated water directly into nearby rivers. Just because water is treated in a sewage plant does not mean that all pollutants are completely removed, and the release of treated water into surface water systems can still significantly degrade water quality. Toxic pollutants, risk assessment, and cost-benefit analysis. Although human feces can be broken down naturally over a period of days or weeks, many organic compounds, such as the banned pesticide DDT, persist for decades, and heavy metal contaminants such as arsenic or lead never decompose. These heavy metals may change chemical form and become benign, but the atoms never decompose. Environmental laws in developed nations regulate the discharge of pollutants into waterways. Yet pollutants continue to enter streams and rivers. Even in situations where waterways are contaminated with very small amounts of toxic non-biodegradable compounds, a great many different pollutants may be found in a single river, and even small concentrations may cause cancer or birth defects. Scientists do not know the doses at which many compounds become harmful to human health. The uncertainty results in part from the delayed effects of some chemicals. For example, a contaminant might increase the risk of a certain type of cancer, but the cancer may not develop until 10 to 20 years after exposure. Because scientists cannot perform direct toxicity experiments on humans, and because they cannot wait decades to observe results, they frequently attempt to assess the carcinogenic properties of a contaminant by feeding it to laboratory rats. If rats are fed very high doses, sometimes hundreds of thousands of times more concentrated than environmental pollutants, they may then contract cancer in weeks or months, rather than in years or decades. Suppose that a rat gets cancer after drinking the equivalent of 100,000 glasses of polluted well water each day for a few weeks. Can we say that the same contaminant will cause cancer in humans who drink 10 glasses a day for 20 years? No one knows. It may or may not be legitimate to extrapolate from high doses to low doses and from one species to another. Scientists also use epidemiological studies to assess the risk of a pollutant. For example, if the drinking water in a city is contaminated with a pesticide and a high proportion of people in the city develop an otherwise rare disease, then the scientists may infer that the pesticide caused the disease and that its presence in drinking water constitutes a high level of risk to human health. Because neither laboratory nor epidemiological studies can prove that low doses of a pollutant are harmful to humans, scientists are faced with a question: should businesses and governments spend money to clean up the pollutant? Some that the contaminant is harmful. Others invoke the precautionary principle that it's better to be safe than sorry. Pollution control is expensive. However, pollution is also expensive. If a contaminant causes people to sicken, the cost to society can be measured in medical bills and loss of income resulting from missed work. Many contaminants damage structures, crops, and livestock. People in polluted areas also bear the economic repercussions of diminished tourism and land values when people no longer want to visit or live in a contaminated area. Groundwater pollution: water in a sponge saturates tiny pores and passages. 2. Clean a contaminant from a sponge. It would be necessary to clean every pore of the sponge that came into contact with contaminated water. Because this is nearly impossible to achieve completely, no one would wash dishes with a sponge that had been used to clean a toilet. Many different types of sources contaminate groundwater. Because these contaminants permeate an aquifer in a manner analogous to the way in which contaminated water saturates a sponge, the removal of a contaminant from an aquifer is both difficult and expensive. Once a pollutant enters an aquifer, the natural flow of groundwater disperses it, forming a plume of contamination. Because groundwater flows slowly, usually at a few centimeters per day, the plume spreads slowly. Most contaminants persist in a groundwater aquifer for much longer than in a stream or lake. The rapid flow of water through streams and lakes replenishes their water quickly, but groundwater flushes much more slowly. In addition, oxygen, which reacts to decompose many contaminants, is less abundant in groundwater than in surface water, thereby allowing the contaminants to persist for years. For example, in 2006, a 25,000-gallon spill of regular unleaded gasoline occurred from underground tanks at an Exxon gas station in Jacksonville, Maryland. The cleanup operation lasted for over 5 years and involved the drilling of 284 test wells to depth up to 615 feet. Over 77 million gallons of polluted groundwater were treated. Because groundwater pollution can persist for long periods of time, the following situations exist despite decades of government concern and action. Up to 25% of the usable groundwater in the United States is contaminated. About 45% of municipal groundwater supplies in the United States are contaminated with organic chemicals. The gasoline additive MTBE is a frequent and widespread contaminant of underground drinking water. According to the EPA, 5 to 10% of drinking water in areas using reformulated gasoline shows MTBE contamination. Wells in 38 states contain pesticide levels high enough to threaten human health. Every major aquifer in New Jersey is contaminated. In Florida, where 92% of the population drinks groundwater, more than 1,000 wells have been closed because of contamination, and over 90% of the remaining wells have detectable levels of industrial or agricultural chemicals. In 2003, the EPA reported 436,494 confirmed releases of dangerous volatile organic compounds leaking from underground fuel storage tanks in the United States. Treating a contaminated aquifer. The treatment, or remediation, of a contaminated aquifer commonly occurs in a series of steps. Eliminating the source. The first step in treating an aquifer is to eliminate the pollution source so additional contaminants do not escape. If an underground tank is leaking, the remaining liquid in the tank can be pumped out and the tank dug from the ground. If a factory is discharging toxic chemicals into the groundwater, courts may issue an injunction ordering the factory to stop the discharge. Elimination of the source prevents additional pollutants from entering the groundwater, but it does not solve the problem posed by the pollutants that have already escaped. For example, if a buried gasoline tank has leaked slowly for years, many thousands of gallons of gas may have contaminated the underlying aquifer. Once the tank has been dug up and the source eliminated, people must deal with the gasoline in the aquifer. Monitoring. When aquifer contamination is discovered, a hydrogeologist monitors the contaminants to determine how far, in what direction, and how rapidly the plume is moving and whether the contaminant is becoming diluted or degraded by bacteria that live in the aquifer. The hydrogeologist may take samples from existing wells and may drill additional wells to monitor the movement of the plume through the aquifer. Modeling. After measuring the rate at which the contaminant plume is spreading, the hydrogeologist develops a computer model to predict future dispersion of the contaminant through the aquifer. To predict dilution effects, the model considers the local geologic structure, the permeability of the aquifer, directions of groundwater flow, and the mixing rates of groundwater. Remediation. Several processes are currently used to clean up a contaminated aquifer. For example, contaminated groundwater can be contained by building an underground barrier to isolate it from other parts of the aquifer. Or, if the trapped contaminant does not decompose by natural processes, hydrogeologists can drill wells into the contaminant plume and pump the fluid to the surface, where it is treated to destroy the pollutant. Bioremediation uses microorganisms to decompose a contaminant. Specialized microorganisms can be developed by genetic engineers to use a particular contaminant as a source of food or energy without damaging the ecosystem. Once a specialized microorganism is developed, it is relatively inexpensive to breed it in large quantities. The microorganisms are then pumped into the contaminant plume, where they attack the pollutant. When the contaminant is gone, the microorganisms die, leaving a clean aquifer. Bioremediation can be among the cheapest of all cleanup procedures. Chemical remediation is similar to bioremediation. If a chemical compound reacts with a pollutant to produce harmless products, the compound can be injected into an aquifer to destroy contaminants. Common compounds used in chemical remediation include oxygen and dilute acids and bases. Oxygen may react with a pollutant directly or provide an environment favorable for microorganisms, which then degrade the pollutant. Acids or bases can neutralize certain contaminants or remove pollutants from groundwater by precipitating them to solid forms. Reclamation teams also can dig up the entire contaminated portion of an aquifer. The contaminated soil is incinerated or treated with chemical processes to destroy the pollutant. The treated soil can then be returned to fill the hole. This process is prohibitively expensive, however, and is used only in extreme cases. Nuclear waste disposal. In a nuclear reactor, radioactive uranium nuclei split into smaller nuclei, many of which are also radioactive. Most of these radioactive waste products are useless and must be disposed of without exposing people to the radioactivity. In the United States, military processing plants, 104 commercial nuclear reactors, and numerous laboratories and hospitals generate more than 2,000 metric tons of high-level radioactive wastes every year. Chemical reactions cannot destroy radioactive waste because radioactivity is a nuclear process and atomic nuclei are unaffected by chemical reactions. Therefore, the only feasible method for disposing of radioactive wastes is to store them in a place safe from geologic hazards and human intervention and to allow them to decay naturally. The U.S. Department of Energy defines a permanent repository as one that will isolate radioactive wastes for 10,000 years. However, this number is totally arbitrary, based on the fact that 10,000 years is so far into the future that most people won't worry about pollution occurring at that time. Actually, radioactive wastes will remain harmful for 1 million years or more because of the long half-lives of some radioactive isotopes. As a result, radioactive wastes could become harmful to human or non-human ecosystems over the course of geologic time. For a repository to keep radioactive waste safely isolated for long periods of time, it must meet at least 3 geologic criteria. 1. It must be safe from disruption by earthquakes and volcanic eruptions. 2. It must be safe from landslides, soil creep, and other forms of mass wasting. 3. It must be free from floods and seeping groundwater that might corrode containers and carry wastes into aquifers. The Clean Water Act, a modern perspective. When it was adopted in 1972, the Clean Water Act set an ambitious agenda for cleaning the nation's rivers, lakes, and wetlands. Have we achieved our goals? The good news is that municipalities no longer dump raw sewage and factories no longer discharge untreated waste directly into our waterways. The bad news is that much of our water remains polluted and most documented violations remain unpunished. For example, a 2009 New York Times study reported that over 500,000 documented violations of the Clean Water Act had occurred over the prior 5 years, yet less than 3% of these violations resulted in any fines or other punishment. In 2004, the EPA reported impaired water quality for 44% of the nation's assessed streams, 64% of assessed lakes, and 30% of assessed estuaries. A 2007 EPA study found that 49% of U.S. lakes contain fish that are contaminated with mercury and considered dangerous for human consumption. By 2008, the EPA listed over 8,700 water bodies in 43 states, including the District of Columbia and Puerto Rico, that exceeded the mercury concentrations limits established by the Clean Water Act. Clearly, meeting these standards is easier said than done. Chapter 13: Glaciers and Glaciations. Introduction. We often think of glaciers as features of high mountains in the frozen polar regions, yet anyone living in the northern third of the United States is familiar with landscapes created by a vast ice sheet that covered this region as recently as 17,000 years ago. In New England, which was virtually covered by ice at that time, glaciers sculpted Maine's rocky coastline and modified the shapes of the northern Appalachian Mountains. The ice also deposited sediment that today forms Massachusetts' famous hook-shaped peninsula and the offshore islands around Martha's Vineyard. Further west, glacial ice carved out the depressions now occupied by the Great Lakes and deposited vast blankets of sediment across much of the upper Midwest. Even further west, glacial erosion deepened valleys and sharpened mountain peaks and ridges in the Rocky Mountains and created the subdued lowlands of Puget Sound and the San Juan Islands in western Washington state. Numerous times during Earth's history, glaciers grew to cover large parts of Earth and then melted away. Before the most recent major glacial advance, beginning about 100,000 years ago, the world was free of ice except for on high mountains and in the polar ice caps of Antarctica and Greenland. Then, in a relatively short time, perhaps only a few thousand years, Earth's climate cooled. As winter snow failed to melt completely in summer, the polar ice caps spread into lower latitudes. At the same time, glaciers formed near mountain summits, even near the equator. They flowed down mountain valleys into nearby lowlands. When the glaciers reached their maximum size between about 24,000 and 17,000 years ago, they covered 1/3 of Earth's continents. Humans, who have been on this planet for about 100,000 years, lived through the most recent glaciation. In southwest France and northern Spain, humans developed sophisticated spearheads and carved body ornaments between 40,000 and 30,000 years ago. People first began experimenting with agriculture between about 12,000 and 10,000 years ago. Formation of glaciers. In most temperate regions, winter snow melts completely in spring and summer. However, in certain cold, wet environments, some of the winter snow remains unmelted during the summer and accumulates year after year. During summer, the snow crystals become rounded and denser as the snowpack is compressed and alternately warmed during daytime and cooled at night. If snow survives through one summer, it converts to rounded ice grains called firn. Mountaineers like firn because the sharp points of their ice axes and crampons sink into it easily and hold firmly. If firn is buried deeper in the snowpack, it converts to glacial ice, which consists of closely packed ice crystals. A glacier is a massive, long-lasting, moving accumulation of compacted snow and ice. Glaciers form only on land, and they derive their ice from regions in which the amount of snow that falls in winter exceeds the amount that melts in summer. Because ice under pressure behaves like plastic and deforms easily, mountain glaciers flow downhill. In many cases, glaciers also slide downslope along their base. Glaciers on level land flow outward under their own weight. Unlike water, glacial ice is capable of moving upslope if it is being pushed from behind by ice flowing downslope from higher elevation portions of the same glacier. Glaciers form in two environments. Alpine glaciers form at all latitudes on high, snowy mountains. Continental ice sheets form at all elevations in the cold polar regions. Alpine glaciers' mountains are generally colder and wetter than adjacent lowlands. Near the summits, winter snowfall is deep and summers are short and cool. These conditions create alpine glaciers. With the exception of Australia, alpine glaciers exist on every continent, in the Arctic and Antarctica, in temperate regions, and in the tropics. Glaciers cover the summits of Mount Kenya in Africa and Mount Cayambe in South America, even though both peaks are near the equator. Some alpine glaciers flow great distances from the peaks into lowland valleys. For example, the Kahiltna Glacier, which flows down the southwest side of Denali in Alaska, is about 65 kilometers long, 12 kilometers across at its widest point, and about 700 meters thick. Most alpine glaciers are smaller than the Kahiltna. For example, Switzerland's Gorner Glacier, shown in figure 13.2, is about 14 kilometers long, about 1.5 kilometers across at its widest point, and up to 450 meters thick. The growth of an alpine glacier depends on both. Finally, during the summer, water melted from the surface of a glacier may seep downward to its base. A glacier also moves by plastic flow, in which the ice flows as a viscous fluid. Plastic flow is demonstrated by two experiments. In one, scientists set a line of poles in the ice. After a few years, the ice moves downslope so that the poles form a U-shaped array. This experiment shows that the center of the glacier moves faster than the edges. Frictional resistance with the valley walls slows movement along the edges of the glacier. Because glacial ice flows plastically, this resistance slows the edges of the glacier down relative to the center. In another experiment, scientists drive a straight, flexible pipe downward into a glacier to study the flow of ice at depth. After several years, the entire pipe has moved downslope and become bent. This experiment demonstrates that at the surface of a glacier, the ice is brittle, like an ice cube or the ice found on the surface of a lake. In contrast, at depths greater than about 40 meters, pressure is sufficient to allow ice to deform plastically. The curvature in the pipe shows not only that ice moves plastically but also that middle levels of a glacier move faster than lower levels. The base of a glacier is slowed by friction against bedrock, so it moves even more slowly than the plastic portion above it. The relative rates of basal slip and plastic flow depend mainly on the steepness of the bedrock underlying the glacier, the thickness of the ice, and the temperature of the glacier. Glaciers located on steep slopes are prone to more basal slip than glaciers located on flat ground. The thickness of a glacier determines the pressure at its base. Because pressure depresses the freezing melting point of ice, a thick glacier will be more prone to develop a layer of water at its base, which will in turn promote basal sliding. Similarly, warmer temperatures at the base of a glacier will produce a layer of water that acts like a lubricant and promotes basal sliding. In contrast, if the temperature at the base of the glacier is cold enough, the glacier can freeze to the underlying substrate, thereby eliminating basal slip and causing the glacier to move entirely by internal deformation. When a glacier flows over uneven bedrock, the deeper plastic ice bends and flows over bumps, while the brittle upper layer stretches and cracks, forming a crevasse. Crevasses form only in the brittle upper 40 meters or so of a glacier, not in the lower plastic zone. Crevasses open and close slowly as a glacier moves. An icefall is a section of a glacier consisting of crevasses and towering ice pinnacles. The pinnacles form where ice blocks break away from the crevasse walls and rotate as the glacier moves. With crampons, ropes, and ice axes, a skilled mountaineer might climb into a crevasse. The walls are a pastel blue, and sunlight filters through the narrow opening above. The ice shifts and cracks, making creaking sounds as the glacier advances. Unfortunately, many mountaineers have been crushed by falling ice while traveling into crevasses and through icefalls. The mass balance of a glacier. Consider an alpine glacier flowing from the mountains into a valley. At the upper end of the glacier, snowfall is heavy, temperatures are below freezing for much of the year, and avalanches transport large quantities of snow from the surrounding slopes onto the ice. More snow falls in winter than melts in summer, and snow accumulates from year to year. This higher elevation part of the glacier is called the zone of accumulation. Lower in the valley, the temperature is higher throughout the year and less snow falls. This lower part of a glacier, where more snow melts in summer than accumulates in winter, is called the zone of ablation. When the snow melts, a surface of old, hard glacial ice is left behind. The equilibrium altitude line, or ELA, is the boundary between the zone of accumulation and the zone of ablation. The ELA shifts up and down the glacier from year to year, depending on weather. Ice exists in the zone of ablation because the glacier flows downward from the accumulation area. Further down the valley, the rate of glacial flow cannot keep pace with melting, so the glacier ends at its terminus. Glaciers grow and shrink. For example, the zone of accumulation in an alpine glacier will grow thicker and the glacier's ELA will descend to a lower elevation if annual snowfall increases and more firn survives the summer without completely melting. At first the glacial terminus may remain stable, but eventually it will advance farther down the valley. The lag time between a change in climate and the advance of an alpine glacier may range from a few years to several decades, depending on the size of the glacier, its rate of movement, and the magnitude of the climate change. If annual snowfall decreases or the climate warms and less firn survives the summer, the alpine glacier will grow thinner, its ella will recede upslope, and the glacier terminus will retreat. When a glacier retreats, its ice continues to flow downhill.